Okay, so today I'll start with another Sturm-Liouville problem. Find the eigenvalues and eigenfunctions of the Sturm-Liouville problem y double prime plus lambda y equals to 0. And yesterday we did an example where the endpoint values were 0, but this time I'm going to give you an example where you have y prime of 0 equal to 0 and y prime of 4 equal to 0. Okay. Solution. Let's start with the case. So a case when lambda is greater than 0. And Sturm-Liouville problem simply means that we are looking for solutions that are not trivial. As you can see, y equal to 0 will satisfy the differential equation, the boundary conditions as well. Right? So it's something that obviously will satisfy, but when we try to solve the partial differential equation using some method called separation of variables, at some point we will need to find non-trivial solutions of such a differential equation. And that's why we're asking that question. Okay, so when case lambda is bigger than 0, you can start with writing the characteristic equation. And the characteristic equation is what you get if you plugged in y equals to r e to the rx. So if you plug in y equals to e to the rx into this differential equation, the second derivative will bring down r twice, creating this r squared, and this lambda will be multiplied. And once you divide it by e to the rx both sides, this is the equation you end up with. And what you get is you end up with, if you move the lambda to the other side, you get r squared equal to negative lambda, and then taking the square root, you get the square root of lambda, but you also get the square root of I, square root of negative 1, which we call as I, right? So you get plus or minus. And in such a situation, we learned that this, when you plug it into e to the rx, you end up with something that looks like Euler's identity, where it creates the cosine as the real part and the sine as the imaginary part. But because you don't want complex valued solutions, you want real valued solutions, rather than trying to work with this, you just take the real part and the imaginary part separately to create the solution, which looks like y equals to a times cosine, no, let's write c1, okay? c1 times cosine square root of lambda times x, plus c2 times sine square root of lambda times x. All right, now let's apply the boundary conditions to see what it means. Now, in order to apply the boundary conditions, because they have derivatives, we will need to differentiate this one before we apply the boundary conditions. So let's try to differentiate. Differentiating cosine gives you negative sine, and because of the chain rule, the derivative of the inside function should be put outside, and the derivative is square root of lambda, so you're going to get c1 square root of lambda sine of square root of lambda x, and then plus c2 square root of lambda times cosine square root of lambda times x. And then you plug in 0, so you have y prime of 0, which will give you negative c1 times square root of lambda times 0, because sine of 0 is 0. And then plus c2 square root of lambda. What's cosine of 0? 1. And this value is given as 0, so that we have 0 equals to c2 times square root of lambda. And because our assumption is that lambda is bigger than 0, this cannot be 0, so the only choice is to have c2 as 0. So if you divide this to the other side as 0 over square root of lambda, lambda is not 0 according to our condition here, and therefore this is going to be 0. So we got c2 at 0. Now, plugging the c2 back in here, we get y prime equals to negative c1 square root of lambda times sine square root of lambda times x. And then now we plug in 4, because that's equal to 0. So I plug in 4 into here because y prime of 4 is given as 0. So that has to equal to, no, there's something, oh yeah, it is, okay. Negative c1 square root of lambda times sine of square root of lambda times 4. Okay. Now, again, the immediate thing we can do is we can just divide both sides by square root of lambda, because we know that that's not 0. And immediately, and also let's just get rid of the minus as well. So if you cancel it away, immediately we get c1 times sine of square root of lambda times 4 equal to 0. We have two things multiplied to give you 0, so either the first one is 0 or the second one is 0. Now, can c1 be 0?
No.
Why not?
Because c2 is 0.
Because c2 is 0, and if c1 is also 0, and if you look at your y, what do you get?
0.
0. Okay? You get 0 for both, right? So that would be giving you a trivial solution. So since c1 equal to 0 leads to y equals to 0, which is trivial, okay, we must have the other one equals to 0, which is sine of square root of lambda times 4 equal to 0. Okay? And when does this happen? When is sine of something equal to 0?
Sine of pi?
Yes. Right. When this thing inside is n pi, you get 0. Right? So we know that sine of n pi is equal to 0, and therefore you have this. And then solving for square root of lambda, you get square root of lambda equals to n pi over 4. And you get lambda as n squared pi squared over 16. Okay? And we also need to find the eigenfunction. So in order to find the eigenfunction, we should go back and see what we have. We already know that c2 is 0. So that's gone. And you have this. And since by eigenfunctions, I'm not looking for all the functions, but just one representative for the entire group, I'll just set c1 as 1. And I just have one solution. And since square root of lambda is equal to n pi over 4, we can say that, let me write it here. It's y equals to cosine of n pi over 4 x would be our eigenfunction, with the eigenvalue being lambda equals to n squared pi squared over 16. So that's our first case. Now, second case, what do we have to do?
We have to check if lambda is equal to 0.
Right, so you have to think about the case when lambda is equal to 0. And for lambda equal to 0, you can now plug in 0 in here to get the differential equation y double prime equals to 0, just simply that. And for this one, you don't want to use the characteristic equation because if you do, you get just 0 and 0, and you don't get two linearly independent solutions, which you're required to find if you want to find a general solution. I mean, there's still a way to do it that way, but that would require another review of what we went through the ODE, so I don't like that. The easier way is just to simply integrate both sides twice, right? If you integrate this, you get y prime equal to what? Some constant. So you just put it as a. You integrate again, what do you get? Y equals to ax plus b. And then, since y prime of 0 needs to be evaluated, we really need this one. So we're going to plug in 0 both into x. But because this is a constant, it doesn't change, and that has to equal to 0. So we get a equals to 0 right away. And also y prime of 4 still gives you a, and that has to give you a equals to 0. So both of these conditions simply imply that a is 0. That's it. Okay. All right. So what does that make y equal to? Y must be what?
A constant.
B, right? B, a constant, right? Okay. So this will be a solution to y double prime equals to 0, and also these two boundary conditions. Okay. The next question is that a non-trivial solution? I mean, it looks very simple, so you might be tempted to say, oh, that looks so trivial, that you might say, but it's not, right? It's not a 0 solution, so we still need to make a note of this. So the fact that there exists, yes?
Like, how did y prime is 0 and y prime 4 equal to a? Like, how do you get that?
Oh, y prime is a. It's a constant.
Yes.
Right? So whether you plug in 0 or 4, it doesn't matter. It will always create a.
I see.
Right? And then I'm just writing these conditions where from here, right? And then that just leads to a equals to 0, a equals to 0. But if a is just equal to 0, then y would just be equal to b. And I'm trying to say that this is a non-trivial solution. So therefore, lambda equal to 0 is or is not an eigenvalue. Which one is it? 0 is an eigenvalue, or 0 is not an eigenvalue? What is it?
Not.
When do you say a value is an eigenvalue? If you have an eigenvector, right? Eigenvalue, you call a number an eigenvalue for the system if you have a non-trivial solution. You have an eigenfunction. Then is this an eigenvalue? Yes. Okay. So this so lambda equal to 0 is an eigenvalue with eigenfunction y equals to 1. We just choose 1. Okay, and third case would be C would be when y is less than 0, right? If y is less than 0, then not y, sorry, lambda less than 0. If lambda is less than 0, you can call that as some negative c squared, and then this equation here, r squared plus lambda should be just negative c squared equal to 0, so that you get r as plus or minus c, which gives you y equals to e to the cx and e to the negative cx as the two solutions, and you put c1, c2. And then you can do, like, apply the boundary conditions, and at the end of the day, you'll see that there's no other way than to have c1 as 0 and c2 as 0. Okay? But my suggestion is that for this case, you can just omit it. Okay? That's because, as I explained last time, if you write this as an operator form, so move the y double prime to the other side and write it as negative y double prime equals lambda y. And then you write this as a second derivative operator with a minus. Then there's a general theory of a Sturm-Liouville operator. This is an example of a Sturm-Liouville operator. And for any Sturm-Liouville operator, the eigenvalues will always be greater or equal to 0. It will never be negative. And that's something that I will prove at some point. Okay, so I mean, I don't want to do the full Sturm-Liouville theory yet because I want to wait until we get to some more complex examples. So right now I'm just showing you the easiest part of the Sturm-Liouville problem. So I haven't proved this yet, but you can always skip the lambda negative because we know that such a differential operator will always have a non-negative eigenvalue. So this one can be omitted. So you just have to do case when lambda is positive and case when lambda is 0, and that's it. Okay. All right, so now we can write down the answer to this question. So what is the answer? Answer is that eigenvalues are lambda equals to n squared pi squared over 16, and or with eigenfunctions y equals to cosine n pi over 4x. Now this seems to be only using the answer to the first one, right? But observe that if you let n equals to, not from 1, 2, 3, 4, but start from 0, when n is 0, lambda is 0, right? So it includes this case. And it even includes this eigenfunction because if you plug in n equals to 0, what do you get? You get cosine of 0. What's that? That's exactly 1. So it includes this case. So when you write down the solution of a Sturm-Liouville problem, it's very important that you write down what n is. Okay? If you look at yesterday's notes, you will see that I did say for the Sturm-Liouville problem yesterday when we didn't have the primes. Yesterday we did the y of 0 equals to 0 and y of 4 equals to 0. There, if you look back, you'll see that I wrote down n starts from 1, 2, 3 without the 0 there. Okay. Here, the 0 does exist because 0 is indeed an eigenvalue. So that's the distinction between the two different types of boundary conditions. Any questions so far?
Right.
Yes.
Like for the lambda is less than 0, how do you end up getting lambda is equal to negative c squared?
So this part. So the way I'm trying to do this is, if lambda is a negative number, then there must be a value c where lambda is equal to negative c squared. Now, I'm doing this for two different reasons. First, eventually when you solve it, you get r equals to c, so you get rid of that annoying square root. So the later on calculations become easier to track. And also, I also know that c squared is always positive, or it could be 0. It's never negative. So if you put a minus c squared, it immediately forces you to say that, it just makes you remember that lambda is in itself a negative number. If you don't do that, then the problem is if you just use r squared plus lambda equals to 0, and you get r equals to plus minus square root of negative lambda, this looks like an imaginary value, but it's not, because lambda itself is negative, so negative lambda is positive. So this is a real value, but it's really confusing, don't you think? Right? So this is a good strategy to handle a negative number.
I see.
But again, you can omit this, so it's not a problem. All right. So we had 3 and a little bit more classes where we mostly did preparation to solving a partial differential equation. Although in the very first class I did solve the wave equation on the real line. Apart from that one example, I've been showing you a bunch of things without even showing you how to solve one PDE that's harder than the wave equation. So now I am ready to present you a partial differential equation, and we're going to solve it, and we'll try to understand how the solution reacts. Okay? So I'll have to come up with some equations today. So the heat equation. So the heat equation deals with how something heats up or cools down. So let's say you have a metal bar. Okay. And to make this a one-dimensional thing, I want to surround it by insulation. Like things like styrofoam. Styrofoam like do not make the heat escape, right? So it's surrounded with the insulation. I'm viewing a cross section, but it's really surrounding the entire rod all the way across, so that no heat is escaping. Right? And then on the two endpoints, you can either leave it exposed to the air so that it will cool down or heat up to a certain ambient temperature, or you might want to do something like putting on ice here. Just like that. So that in terms of Celsius, the temperature at the endpoints will be 0. Okay. And then we want to think about the following question. If initially the rod is like 20 degrees Celsius, which is kind of close to like 60 something degrees room temperature, and then you put ice at the endpoints, then how can you describe the distribution of the temperature inside the rod at time t? And you already have some idea, right? So initially it will be 20 degrees Celsius everywhere, right? But then the moment it touches ice at the end, the endpoints will quickly cool down, but it will take some time for that temperature to inside to dissipate away. So after some time it's going to be like that, and then gradually everything will cool down, and that's what's going to happen with this system, right? And what we want to do is we want to actually simulate this this temperature distribution of the rod by coming up with the partial differential equation, right? So let's try that. And you know, in many textbooks, including the ones that we have, starts from Newton's cooling law. So Newton's cooling law. This states that the temperature of an object will change with respect to the difference between the ambient temperature and itself, and it's proportional. So if the difference between the ambient temperature to itself is big, then the temperature will rise or decline very fast. If this value is small, then it's not going to change that much. Okay, so that's the Newton's cooling law, and then you apply this, and then there are some arguments to make, and it takes like several, no, not several pages, maybe like 2 pages to actually derive the heat equation. But I don't feel like you get much intuition behind the heat equation going from here. So rather than that, I'll just make an argument from heuristics, like from your intuition. Right? So suppose you have a heat distribution like that. Then over here, at that point, do you think the the temperature will go up or down? Here. If the heat distribution is like this, at this moment, a millisecond later, would you find this point to have a higher heat or less heat? Higher temperature, right? Because you have surrounding ones, right? So eventually, everything is going to even out. You're going to have something that's flat, right? Okay. So you know that it's going to go up. On the other hand, if the heat distribution is like that, and you have this point, what do you think is going to happen? It will go down, right? So, let's say uxt is defined as the temperature at location x of the rod at time t. Okay, so, and our goal is to figure out what uxt is for all times and all the locations on the rod, right? And what we're trying to do is that we're trying to say that du dt, so that's the rate of change of the temperature, right? If you differentiate, derivative have the meaning of the rate of change, right? So the rate of change of the temperature should be positive if it's concave up. Right? If it's concave up, then it should go up, right? And du dt should be negative if concave down. Right? Not only that, if the concavity is very sharp, it would go up very fast, don't you think, right? Yeah. If the concavity is kind of like, almost like a straight line, it's not going to change that much. Now, you might think that, what about the first derivative, like the slope? Would that do anything? And actually it doesn't, because here's an example. If you have a rod, and you keep this as ice so that this is kept at 0 degrees Celsius, and you leave this exposed to the room temperature, which is 20 degrees Celsius. And if you leave this rod for a long time, then the temperature here will be stabilized as a straight line, wouldn't you think, right? Yeah. And this will go forever. Right? If there's always ice touching and always 20 degrees, then the stabilized temperature distribution at time t equals to infinity will be a straight line. And in that case, at any point, the temperature won't go up or down. So it has nothing to do with the first derivative. See, the change of the temperature in this case will only have to do with the concavity. But how do you measure concavity? What gives you concavity? Second derivative, right? Second derivative gives you concavity. Right? Now, in calculus, have you seen this picture, like here?
Yes.
You've seen this? Oh, okay. All right. What does this mean?
I've seen it. I haven't remembered what it means,
okay.
but like
It is concave up, right?
Yes.
Two i's means it's the second derivatives. And if the second derivative is positive, it's concave up. Right? If the second derivative is negative, it's concave down.
Yeah.
That's what this. It's just to memorize stuff. Right? All right. So we know that this has to do with the second derivative in space, in the x direction. Okay. So it's really about. Oh, sorry. Because there's also x and t. I made a mistake here. This should be partial derivative. Sorry. So this has to do with the second derivative in x. So here's what we just found out by using this intuitive argument. If the second derivative is positive, that means it's concave up, then the rate of change of the temperature will be positive. If the second derivative is negative, this picture here, then it's concave down. And if it's concave down, the rate of change of the temperature will be negative. Right? And because we also know that depending on how harsh the concavity is, the faster the change of the temperature will be, we know that round u round t is proportional to round squared round x squared u. You know, at some point it's too much to write down round all the time, so I'm just going to write the shorthand, which is just simply ut uxx. That's a lot simpler, right? Okay. You know this fish-like thingy is proportional. So if this increases, this increases. If this becomes negative, this is also negative, and so on and so on. And when you have two sides being proportional, you can change this into an equation. How do you do it? How do you make a proportionality argument into an equation? You do this a lot in physics.
Add a constant.
You put a constant in front, right? You put k times uxx as ut. Very good. Yeah. So that's the heat equation. Okay. Now, once you are convinced that this will be the governing equation for this one-dimensional rod, then you can continue on to describe the other parts of the equation. So here's the full description of this system. First of all, ut should equals to k times uxx. And for exam purposes, I might give you the value of k explicitly, but in many cases, this is something that's, that has to be figured out by experiment. Okay? Because it all depends on the makeup of the metal, and also the size will also matter, and so on and so on. So it really is case by case. Now, let's talk about the boundary conditions. So I'm saying that for all times, the value at 0 is always 0. Right? The temperature at 0 is always 0. And u at L, let's say this length is L. Okay, so this left side will be x equal to 0, and this right side will be x equal to L. Okay? So u L t is equal to 0. Okay, and then so this should be true for all times t greater than 0. And then u x 0. What does this mean?
It means that the time is 0.
When time is 0 and you want to know the distribution of the heat at that time, right? And I say it in words that if this is like initially 20 degrees Celsius, you just put 20. Okay. And that should be true for x between 0 to L. And this one should hold for all times and also every x. And this is a heat equation that you can solve. So I promise we will be solving this, but maybe not today, because I want to solve another one. Maybe today, I don't know. Here's another kind of setup. What if you had a metal bar, again insulated, so that it's still one-dimensional problem. If it's not one-dimensional, then this has to be altered because the temperature will actually depend on not only x, but maybe towards the rim of the bar, it will have lower temperature because it's losing heat at the end. So you'll have the function u as depending on not just x and t, but x, y, z, and t. So you will have a different equation that's harder than this. We will solve that as well later, okay? So again, insulated. And the insulation, as I said, is just to make the problem as one-dimensional. And let's say that the initial temperature is like 0 degrees here, but then over here, 20 degrees here. Okay. And we'll just have this endpoint as x equals to 4, x equals to 0. Okay. So I'm actually using more concrete numbers just so that we can solve it easily. And then for the boundary conditions, this is what I want to apply. I want to say that this end is again insulated. And this is also insulated. And this time you will have to, it's a bit harder to imagine what's happening at the endpoints. So here's what happens. This is the initial condition, and this is the initial condition. And then if you let this evolve just for a minute, just like for a few milliseconds, then because this side is insulated, this side is insulated, what's going to happen is that eventually it will try to even out along the entire bar, right? It's going to even out through the entire bar. And the change will happen at the endpoints because, see, the temperature here right here will try to go down because at this point, that's the highest point. So the highest point will try to go down, so this will go down. And this one will go down, and in the middle there won't be much change because the second derivative is 0 here, right? It will be originally just the boundary conditions that will force things to be going down. And once it makes it go down, then what happens is that you do introduce concavity, right? And because it's slightly concave down, this will make it go down as well. Here it will be concave up, so it's going to go up, and therefore the changes will be broad inside. Okay? So eventually everything will try to balance out to a common answer, like it will be degree 10 at time infinity, right? Where this will just keep going up and it will keep going down, and everything will become 10. Yes?
Remind me what the x's mean again, like what they represent in this case?
Oh, this is x, and this is the value of u.
I see.
So this is the temperature at each location of the bar. Okay?
Okay, so x represents the temperature.
Yes.
U represents the temperature, x is the location.
Okay.
Okay, yeah. Now, at any moment, if you stop, you have to think about what it looks like. It will look something like this, right? And what do you think the slope at the end point will be? The slope at the end point will be always 0.
Okay.
Okay? Yeah. Will always be 0. So for insulated boundary conditions, what happens is that the boundary conditions. Oh, by the way, this has names. So this one is called the heat equation. This one's called the boundary conditions. And this one is called the initial condition. Right, so the boundary condition is that if you take u and look at the slope in the x direction, it will be 0 at both endpoints. That's what's going to happen. So that's the main difference. Here, the boundary conditions make the value equal to 0, whereas this boundary condition gives you the derivative equal to 0. And they have names. If the values are given, this is called the Dirichlet boundary condition. So, Dirichlet boundary condition, where value of u is given. On the other hand, this one is what we call the Neumann boundary condition, where the derivative of u is given. Okay, and then there's still another kind of boundary condition where you have a mix of this. So you might have like this plus this equal to some value. That's called Robin boundary condition, and I'm not sure if we have time to do that. Probably not. Okay, but there is still another boundary condition. Okay, now let's try to write this system as a heat equation. So it will be ut equals to k times uxx, and then boundary of, let's just be consistent with this notation, ux 0t equals to ux 4t equals to 0, where this derivative with respect to x being 0 means it's insulated. Okay. So another way to think about it is like that change of u with respect to x is how much heat you're losing to the boundary. If this is given as, say, -1, that means that you're always losing heat at constant rate. So because this is set to 0, that means you're not losing heat at all. Okay. That's another way to think about this boundary condition. Okay. So this means it's insulated endpoints. So for t greater than 0. And then u of x0 should be this function that we were talking about initially, right? What was that? Well, it's a straight line, and so it's a straight line passing through the origin, so it must be y equals to ax. What should be the value of a? What do you think? Anyone quick with mental math? I have a straight line, and it has to pass through 4, 20. 5, right? Yeah. That's the initial condition. So that would be our initial condition. And I hope to solve this one today. But because wave equation is so similar to the heat equation, let me also talk about the wave equation. So for the wave equation, it's like this. You tie a string, so the 2 points are fixed, right? It's like a guitar string. How many of you play guitar here? Mm-hmm. Well, I play guitar, so I know what this means, right? It's 2 endpoints fixed, and it's a vibrating string. And imagine what's going to happen when the string is in this configuration. So what's going to happen here? It's a trick question, actually. What do you think is going to happen to this point? If you see a snapshot of a vibrating string, right? And you see that it's right now in this configuration, okay? What do you think is going to happen afterwards? Huh? You would think it goes up, right? But actually it's not true, because think about a vibrating string. So it's like going back and forth like that. Okay? So if the still shot, if the snapshot was right here, right? We don't know if this snapshot was taken when the string was going this way or going up. So just from the configuration itself, we can't talk about what happens to the actual string a moment later, right? So in this case, let's define uxt as the following. Uxt will be the displacement of the string, or actually vertical displacement of the string at location x at time t. So if this is 0 and the length of the string is L, and if this is like somewhere middle way, it's like half of L, u of 1/2 L, and let's say time t equals 0, this will be some negative value, right? So I don't know what this displacement is, but if I call this as negative change of y, or let's measure this and say it's like 3 millimeters. You could do something like that, right? So it's like a moving pendulum, right? Moving pendulum. So if you're somewhat away from the origin, you don't know if it's going to go this way or that way, but it does tell you something about the motion. What? In a moving pendulum, what does it say if you take a stop motion? It doesn't tell you the velocity of the motion, but it tells you, This concavity is not going to tell you the velocity of this string. We don't know if it's going to go up or down, but rather it tells you
Acceleration.
acceleration, right? Because why? Because if it's like this, it builds tension, right? You do know that there's a force building up to push it that way. It's just that you might have a velocity that's still going downwards. So it might go this way, but when it's going down this way, the tensions build up trying to put acceleration that way. So eventually, at this lowest point, the velocity turns to 0 because you always have this upward acceleration, and that's when it goes up. Right? So what you know is that this is not in the control of the velocity itself, but it has the control of the acceleration. Okay? Now, how would you write down the acceleration if you know u is the displacement? Displacement, if you differentiate displacement, you get velocity, and you differentiate velocity, you get acceleration. So what should I put here? You're dividing u by, you're differentiating u by what variable? U is a function of x and t, so it's just a multiple choice. Pick your choice. Which one is it? Huh? No, xx would be just the shape, right? It's the derivative with respect to time that gives you velocity and acceleration. So what you need is you need to differentiate twice in t. Okay. And then you see that this gives you the acceleration. Acceleration should be proportional to the tension built up in this string, and the tension is again given by the second derivative. Okay? So again, you will see that if this is positive, acceleration will be positive because it's pushing it up, right? If it's like there, so that it's concave down, if the second derivative is negative, this will also be negative because there's a tension building up so that the acceleration is going down. And if you agree that their signs should match, you can write this, and then you can now write this as a differential equation. How would you write that? UTT is? How do you change a proportionality equation into an actual equation? What do? Constant times uxx, right? Now, although you can put k here, it's conventional to put c squared here. And that was the actual equation we solved in the first lecture. Okay? And I said, oh, that c, in some cases, it's like the speed of light, and it could be like special relativity and stuff. Because like light is a wave as well, right? So, but this one is what you want to write because you want to make sure that when uxx is positive, utt is positive. So making c squared ensures that. Okay? But also when you actually solve it, at some point you end up having to take the square root, and it's easier to do the calculation. If you have k not c squared, then you end up having square root of k all the way around, and it becomes very messy. You don't want that. So that's why people write c squared for this one. Okay? So compare that with the heat equation, which is ut equals to k times uxx. By the way, even this one, you're always assuming the k is positive. If k is negative, that's not physical. You have something that's really strange. Okay? In fact, if k is negative, you might not guarantee the solution of the differential equation. So this is the heat, and this is the wave. And you can see that one deals with the first derivative, whereas this deals with the second derivative. Now, if you have a second order differential equation, you actually need to provide how many initial conditions? If you have y double prime, a differential equation, right? Then you need to provide y of 0. Is that it? Does that uniquely define the answer? What else do you have to do? Y prime of 0 must be supplied, right? You need two things as an initial condition in order to get a full solution, right? So for this one, the boundary condition will always be the Dirichlet type, because it's fixed at the endpoints. Right? But the initial condition will now be two of them. So you'll need to provide one for the ux of 0, and another one for ut x of 0. And it'll be like that, okay? So that will be a system describing this, okay? When you pluck a string, some of you might play violin. How many of you play violin? Took lessons when you were a little kid, no? Okay, that's not fun. Okay. Well, if you pluck a string, if you pull the string and then you release it, then if you release it, the initial velocity will be 0. So initial velocity distribution will be 0, and you'll have some displacement graph here, and then you can see what happens. Okay. Now, the way I'm describing these are totally heuristic. If you want to challenge yourself, try to read the solutions, the derivations in the textbook. Although it's kind of hard, but one thing that you will get out of reading the solutions in the textbook is that you will find that this description is not totally accurate. There is actually at least for the string tension case, there is an involvement somewhere where you approximate a sine function by a tangent or something like that, or vice versa. I can't remember exactly. And therefore, if you think this is an exact description of a string vibrating, it will give you some non-physical answers. So one thing is, like, if your initial condition is like this and you make it vibrate, then it will be going back and forth like that. You'll always have this point which is not differentiable, but that doesn't agree with the real life string, because if you pull it and release it, usually it quickly the higher frequencies are lost and it becomes round kind of vibration. So that's why this is not perfect, but if you can also derive wave equations for the case when you have like a wind pipe. Like if you have, you learn this in physics, if you have a what do you call it, hollow pipe, right, with one end closed, and you put air waves there, then the air here will vibrate, and at each point you have a displacement of the air, and you can represent that displacement of the air, which is left or right, as a vertical graph, and you have this type of standing waves. You've seen that. You remember this kind of graph in your physics class? All right. like that, like that one, right? Okay. So for that one, you can still derive it in the same manner and you will get the same equation. So when you come up with wave equations describing the air waves like that, or even the ones from general relativity, you will get this one without any approximation. So for those, this is actually even better representation of what's going on than the string. Okay. All right. So we will eventually solve this as well. So now let's try to solve this equation. So I'll title it Solution of the heat equation by separation of variables. And I'm going to just write this, but I'll give you a specific value of k because that makes it easier to think. So let's just say that, so example, solve ut equals, so let's just say 2 uxx u x of 0 t equals to u x of 4t equals to 0, and u x 0 equals to 5x. So let's solve that. And you're supposed to have all these other boundary conditions for t, but I'm not so careful. Okay, so let's try to actually solve this. Solution. I think I say this several times already, but let me say it again. We're really not trying to solve differential equation. We're just trying to make a good guess, something that works. Okay. If we manage to find a solution that satisfies all the conditions, then we know that is the answer because there's a uniqueness and existence already proved for this type of differential equation. Now, there are cases where uniqueness and existence is already there, but you can't even come up with a good handwritten solution. In that case, computers can be used to solve, but then you would be worried whether that approximate solution would be good enough, and in that case, the stability of the system would be another issue. Okay. All right. So, but this one we can actually solve by hand. So we will solve by hand. And what we're going to do is we're going to take some steps. So step 1, instead of trying to solve everything, you want to take the first 2 and try to find building blocks of the solutions. It's just like, you know, when we did yesterday, y double prime y plus y equals to 0, and y of 0 is something, and y of 4 was equal to 0, something like that. What did we do? We first found the building blocks of the solution. We found out that cosine of x is a solution and sine x is a solution, right? And then once you find these solutions, we take linear combinations or the superpositions of the solution. That's the general solution. And then to this, you apply these conditions to figure out what happens. Okay? See, that's your initial condition. So the exact same kind of approach is done here. This is an initial condition. Leave that out of the picture. Just try to find all the possible solutions that's going to solve this. And find solutions that are simple enough so that you can just take linear combinations of them and still satisfy these. And then among them, find the ones that will satisfy the initial condition. That's our goal. Okay? So this step 1, what we're going to do is find all non-trivial solutions of the heat equation and boundary conditions in the form, and this is actually the core idea, in the form u of xt equal to x of x, t of t. Where capital X is a function of x only, and capital T is a function of t only. So, in other words, x is a function of x only, and capital T is a function of t only. So you're trying to look for a solution that looks like a function of x times function of t. Now, who would ever think of such a thing? Well, it turns out that some people working with this a lot realize that for certain solutions, for some nice initial conditions, you have a so think about something like this. Okay, for a nice differential equation like this, they observed, oh no, not this is a so something nice like that will not only satisfies these two, but if you let it evolve, it will evolve like all it is doing is like it's just constant times the shape of the function doesn't change. It's just some multiple of the original one. They found that certain functions look like that. Okay, so in that case, the shape is preserved, and this just controls what constant to be multiplied at some time. That's what they figured out. Yeah. That's all I want to say at this point. All right. So that's our goal. Okay. So what we did was we became less ambitious. Rather than trying to find everything, just trying to find the answers to the first two, and then we became more specific about the form of the solutions, and that actually being more specific makes it easier to find them. Okay. So you're narrowing down your searches. Rather than looking for any function that looks like this, look for the ones that can be represented like this, so it's easier to find. So now let's plug it in and see what we get. Okay, so first, when this is plugged in on the left side, what is ut equal to? If you take this and if you differentiate by t once, what do you get? Does this change?
No.
No. How about this one?
Yes.
Yes. What happens to it?
T prime.
T prime t, right? Okay. And xx would be what?
T x double prime.
X double prime t of t, right?
Mm-hmm.
So now you plug it into here, you get x of x t prime of t equals to 2 times x double prime of x t of t. So that's what happens to the heat equation. Okay. Now let's apply this one. What is ux dot then? What's ux?
Prime
X prime and t, right? That's you differentiated once in x, right? But you're plugging in 0 and t. So what goes in here?
0,
0. What goes in here?
t.
T. Okay. What about this one? What happens there? X prime 4 t of t equals to 0. Okay? And we don't care about the initial conditions yet. We're just doing these two, right? Okay, next. If two things are equal to 0, right? Then it's either x prime of 0 equal to 0 or t of t equals to 0. Okay? But I don't like t of t being 0. So t of t cannot be 0 because what? Huh? Because we have the non-trivial condition. We don't want to find this trivial solution. Of course, 0, 0 would satisfy this for everything, right? We want non-trivial solutions. So because we want non-trivial solutions, we cannot have t of t as 0. So we need non-trivial solutions. Okay. So that means x prime of 0 must be 0, and x prime of 4 must be 0. Okay? Now let's look at this one. Let's see what that does. And this is a part where I think is the real genius of the solution. I mean, you give this problem to any smart person, and they would be able to work out probably about this much, but they're probably stuck here. They wouldn't know what to do here. So you really need to know this trick. The trick would be to divide both sides by kxt. Okay. So maybe I should write it here. Divide both sides by kxt. So that's the idea. So you want to divide by 2 times x of x, t of t, 2 times x of x, t of t, so that x of x will cancel and t of t will cancel. And you get the following thing. So maybe I should write it over here. We have t prime of t over 2 times t of t equal to x double prime of x over x of x. Yes?
What division did you just do there? Like, why did you write it that way?
Oh, we're trying to divide by kxt, right?
Yes.
K is what in this problem?
K is 2.
2, right?
Okay.
And by x mean x of x and t of t. So I'm dividing both sides by 2 times x of x times t of t.
I see.
Yeah. And once you do that, you see that some things are common, so I cancel them out. And once you cancel them out, this is what you get. Oh, you also cancel out the 2 as well on the right side, right? This is what you get. And initially, you don't see anything strange, but if you think about this for a while, you do see that something funny is going on, because the left side is a function of t only, and the right side is a function of x only. And if you think about what kind of function can be called a function of x and as a function of t, you realize that there isn't much choice. So let me say it like this. If you have something like t plus 2, what's that? That's a function of t. Can that be a function of x? No, that's definitely a function of t only. Okay? If you have 2x plus 5, what's that? That's a function of?
X.
It's not a function of t. So what kind of function can you write so that you can say it's a function of t or a function of x? What can you do?
Constant.
Yeah, a constant. If you just have like 5, just 5 here, if that's a function, can you call this a function of x?
No.
Yeah, you can. It's a function of x. It's a constant function of x, right? You can just say this is f of x, no problem, right? Yeah. Yeah. Can you say this is a function of t?
Yeah.
No problem, right? And in fact, if you think further, you see that the only way that you can call a function of x and function of t is when it's equal to a constant. It's something like some baby toys for toddlers when they're just barely walking. They have like some things like star, dial, and there may be like a diamond dial here, and babies would like turn things, right? Yeah. And maybe this is like a walker, and they're trying to walk, and they might do this just so that they're controlling something, right? But what they realize is that they change this and nothing's happening, and they change this and nothing's happening. If a function is not doing anything, what is that? That's a constant function, right? The reason I say that is because if you just say initially, oh, let's just call this a function of x and t, but then if you look at this, you're seeing that this doesn't change its value when you change x. It's like this x where you change, because it's a function of t, it has nothing to do with x, so it doesn't change at all. And then this one is saying that this doesn't change the value when you change t. You change the dial of t, it doesn't change. So if a function of x and t doesn't change its value when you change the value of x or t, what is that? Constant. So that's like the argument. So that's like the hardest argument here, but then the rest of it kind of follows from everything that we learned so far. Okay? So that's a constant, and what we're going to do is we will always name this constant negative lambda. Right? Why negative lambda? You'll see. Okay. So we're going to have t prime of t over 2t equals to negative lambda, so that t prime of t equals to negative 2 lambda t. And we're going to have x double prime of x over x as negative lambda, so that if I multiply this and bring it to the left side, we get x double prime plus lambda x equals to 0. Now you see why we're doing this, right? The naming of the constant as negative lambda does lead to something that we've done before, right? Okay. Yeah, I'm suppressing x. X is still a function of x, okay? I'm just not refusing to write parenthesis x. So, look at this one. And look at this one. When did we solve that? When did we solve this? Huh?
In the beginning of class.
In the beginning of the class, we solved it, right? Y double prime plus lambda y equals to 0 with that, okay? So, this is the Sturm-Liouville problem with y prime of 0 equal to 0 and y prime of 4 equals to 0, right? And we're looking for all non-trivial solutions. And that immediately tells you what lambda could be, right? So here I'm quoting our earlier result, okay? So here's our earlier result. So we solved this previously with the answer as x of x must equal to cosine of n pi over 4x, and lambda is equal to n squared pi squared over 16, where n goes from 0, 1, 2, 3. Right. That was our result in the beginning of the class. Okay, so that's nice. How about this one? How do we solve this? Well, you know, this one again, it's this is a constant, so we know that such a differential equation, if you have a differential equation that's linear and you just have some constant multiples, everything looks like e to some power of x, right? Yeah. So if we say t of t looks like e to the rt, sorry. This time I have to say t because it's a function of t. Right? What is t prime of t? R times e to the rt, right? And that has to equal to negative 2 lambda t of t, but t of t is e to the rt. So this one here is negative 2 lambda t of t. So these two have to be the same, cancel both sides, and we see that r must be negative 2 lambda. Right? And therefore, you put it back in here, we see that t of t must be e to the negative 2 times lambda is n squared pi squared over 16 t. Okay? Yes?
Is that part of the exponent, or is that just...
Oh, this is all part of the exponent. This is all
okay.
on top. Okay. Now, actually, the general solution is some constant times. And even this one, there's some constant times. But when you multiply them, it's still some constant. So here's the answer to our step 1. Okay. So step 1 has the following conclusion, which is that u of xt looks like some constant times e to the negative 2 times n squared pi squared over 16 times t times cosine n pi over 4x. And we see that these are all the non-trivial solutions that looks like a function of x times function of t. Now let's summarize this a little bit so that you would know what to do later. So for these type of heat equations, we see that always t of t will end up being some constant times e to the negative k lambda t. Okay? And x of x, I don't know. It's depending on whether you have Neumann boundary conditions both sides. In that case, it's some cosine of something for Neumann. And if it's a Dirichlet boundary condition with endpoints being 0, it would be sine of something. Dirichlet. Now, there still could be other kinds where you might have like Dirichlet on one side and Neumann on the other side. You might insulate one endpoint and make one part a 0. In that case, you get other complicated ones. So that's something nice to remember to help you out with the calculation. All right, let's continue on. All right. So we got these building blocks of the first two. Now, what would be the general solution of the first two then? What do you do? See, is this just, did we find just one solution? No, we found infinitely many of them, right? Because it's n equals to 0, 1, 2, 3. All of those are solutions for n equals to 0, 1, 2, 3, and so on. So we have many, many solutions. What do you do with them? Once you have many solutions, what do you do with them to get the general solution?
The summation.
Huh?
The summation.
Summation. You take linear, you take the superposition of solutions, and you get a general solution, okay? And it really has to do with the fact that these conditions are linear. If you have two solutions, the sum of the two solutions will still satisfy the heat equation. The heat equation is a linear differential equation. And by the way, we will only be solving linear partial differential equation here, because once it becomes nonlinear, it's really tough. Like it's somebody's PhD thesis to solve a nonlinear differential equation. It's really hard. So it's linear, so we can add them to solve the heat equation. And even this boundary condition will still be satisfied. If you have two solutions satisfying this boundary condition because it's 0, and 0 plus 0 is 0, the sum of the two solutions will still satisfy this condition. Now what's not so easy is if this is non-zero. If this is non-zero, then if you have more complicated boundary conditions, then you can't simply add, then you have to do something more. Okay? All right. So that's going to be step 1. So the ultimate conclusion of step 1 is the general solution of the heat equation plus the boundary conditions would be uxt equal to C0 plus summation of n equals to 1 through infinity of Cn e to the negative, let's just write down n squared pi squared over 8 t, because 2 over 16 can be reduced like that, times cosine n pi over 4 x. Now, you might wonder why I put C0 here. That's because when n is 0, cosine 0 is 1, and e to the 0th power is 1, so you just get a constant term. So I just wanted to write that as a separate thing here. You don't have to. You can just write it as starting from n equals to 0 to infinity. That will be another way to write it, but it will be hard to do a calculation afterwards if you do it that way. Okay? So this is really, indeed, all of the sums of the solutions that look like this. We add everything that looks like this as this. Okay. What's left for us to do now? Yes?
Did we make use of the initial condition?
We haven't done it yet, so now we have to do the initial condition. So step 2, find C0, C1, Cn that satisfies the initial condition. Okay? So let's do that. We plug in u of x0. Okay? So plug in t equals to 0 both sides. Then ux0 gives you 5x. On the right side is c0 plus summation of n equals to 1 through infinity Cn. What's e to the 0th power?
What?
Yeah, you're plugging in t equals to 0, so when t is equal to 0, this becomes 1, right?
Mm-hmm.
And you get cosine n pi over 4x. Okay. Now, where did we see this before? Now it's kind of clear why we did all these other kinds of math before, right? What is this thing called? It's the Fourier cosine series. Okay, so we just have to find the Fourier cosine series of 5x. So let's do that. The formula for the Fourier cosine series is that you have a0 equals to 1 over L integral from 0 to L of f of x dx. And an is 2 over L integral from 0 to L of f of x times cosine n pi over L x dx. Okay. So what? Well, what's the value of L for us? L should be 4, right? This is 4 and 4, then it matches, right? So let's actually do the calculation. So we have A0 equals to 1 over 4, integral from 0 to 4 of 5x dx, which is 1 over 4 times 5 over 2 x squared, plug in 4 and 0, and it gives you 10. So 4 squared is 16, 16 divided by 8 is 2, 2 times 5 is 10. For an, we have to do 2 over 4, 0 to 4 of 5x times cosine n pi over 4x dx. Okay? And then we can just use the tabular integration. Plus minus d integral 5x, differentiate you get 5, differentiate you get 0, cosine of n pi over 4x, integrating cosine gives you sine, but you have the reciprocal of n pi over 4, so it's 4 over n pi sine n pi over 4. By the way, this is very similar to the quiz question that we did yesterday. You integrate sine, you get negative cosine. Another 4 over n pi comes up, so it's 16 over n squared, pi squared, cosine n pi over 4x. Sine alternates. And then you have to do this, this. The last one also has to be multiplied and integrated, but it's 0, so we don't have to do that. Okay, so the result is that we have you still have 2 over 4, don't forget. Okay, so 2 over 4 is outside. 5x times 4 is 20, so it's 20x over n pi sine n pi over 4x. Okay, and then 5 times 16 is 80. Negative and negative is plus, so it's plus 80 over n squared pi squared cosine n pi over 4x. And then you have to plug in 4 and 0. Now 2 over 4 is 1/2. When 4 goes in here, you get sine n pi. What's sine n pi? 0. When 4 goes here, 4 and 4 cancels, you get cosine n pi. What's cosine n pi? Negative 1 to the nth power, right? So when 4 goes in there, you end up with 80 over n squared pi squared, negative 1 to the nth power. Okay. Now when you plug in 0, sine 0 is 0, cosine 0 is 1, so you have to subtract this. And then when you factor out the 80 over n squared pi squared and divide by 2, 80 divided by 2 is what? 40, right? 40 over n squared pi squared. And you have negative 1 to the nth power minus 1. Okay. So now where are we at? We found the A0s and ANs, and we have 5x now equals to A0, which is 10, plus summation of n from 1 through infinity of 40 over n squared pi squared of negative 1 to the nth power minus 1 cosine of n pi over 4x. Now compare this right here with this. That tells you what C's are, right? What's C0? 10. C0 is 10. What's Cn? it's the coefficient of this cosine, right? So it's 40 over n squared pi squared, negative 1 to the nth power minus 1. And therefore, we figured out all the C0s to Cn's. It goes right here. So now we can write the answer down. So the answer will finally be U xt equals to 10 plus sigma n from 1 through infinity of 40 over n squared pi squared, negative 1 to the n minus 1. More room here. E to the negative n squared pi squared over 8t cosine n pi over 4x. That's the solution. Okay, so let's recap what we did today so far. So what is separation of variables? Separation of variables, usually denoted as SOV. Step 1, find all solutions of the form U xt equals to x of x, t of t. Now, remember that wave equation also had x and t? You can solve the wave equation in the exact same way. Just using this. You can solve it in the exact same way. And then step 2, use Fourier series, Fourier sine series or cosine series to find the coefficients. And the crucial step at some point is over here. There's this crucial step where you divide by kxt, or for wave equations, we'll be dividing by c squared xt, and that's going to give you some Sturm-Liouville type of problem which you solve. And depending on what type of solutions you get, if you get sines, you need sine series. If you get the cosine functions, that's the eigenfunctions, you need to do the cosine series. Okay. Now, there's some additional stuff that you want to think about in this solution. What does this do? When t becomes bigger, what happens to this function? You have some really large negative value, right? For big T, right? So what does it do? What is e to the negative infinity? 0, right? E to the negative infinity. And in fact, because it's exponential, it rapidly decays to 0. Okay? It decays to 0 very rapidly. Okay? So, observation. If you send limit of t going to infinity of this uxt above, what would you get? This will be all 0, right?
Mm-hmm.
So what would happen to this part?
The entire thing will be 0.
Except
Except 10.
10. Now, does that agree with our intuition about what the heat distribution should be doing? So as I explained, it's original distribution of heat that looks like 0 here and 20 here, right? 20 degrees and 4, right? And then when you let it evolve with respect to time, you're going to get something like this, and eventually everything will be like averaged out at 10, and when it's 10, there won't be any more changes. So that's what you need to see. Because 10 is the average of 0 to 20, that's kind of obvious, right? Okay. All right, now let's try to solve the other example that we tried. So let's try the heat equation. Let's put 5 uxx, and then u of 0t equals to u of, what was the, can somebody tell me what the Sturm-Liouville problem we ended with last time was? Let's see. That was the ones that came up with a sign. Oh, a sign, right? Yeah. Oh, it was also 4. Okay. So 4t equals to 0. And the reason I like this is because last time we did the following: y double prime plus lambda y equals to 0, with y of 0 and y of 4 equal to 0 gave us y as sine of n pi over 4 x, and lambda would be n squared pi squared over 4 squared, where n starts from 1. Okay? So that's something that we obtained last time when we solved the Sturm-Liouville with the value at the boundary being 0. So that's why I have this. Okay? And u, initial condition, let's just say x0 is flat out 20. All right. Solution. Again, step 1. We said uxt equals to xx tt. And because we don't have much time, let me just try to accelerate a little bit. So when you plug this into the heat equation, you have x of x times t prime of t equals to 5 times x double prime of x t of t. And we have to divide both sides by kxt, so it's 5 times xx tt, 5 times xx tt, so that when you cancel, you have t prime of t over 5t equal to x double prime of x over x of x. And you make an argument that you can't have a function to be both a function of x only and t only. That's the only time that can happen is if it's a constant, so we let it equal to lambda. So that you have t prime equals to negative 5 lambda t, whose solution is t equals to e to the negative 5 lambda t. And you also have x double prime plus lambda x equals to 0. now, if you plug in to here, you get x of 0, t of t, equals to x of 4, t of t equals to 0. And again, t of t cannot be 0, or else u just becomes 0, which is a trivial solution, so we don't like that. Therefore, x of 0 is equal to x of 4 is equal to 0. And then, although you really have to solve this Sturm-Liouville problem, finding all non-trivial solutions of this, we're just going to quote what we did last time, so that we know that x of x must look like sine of n pi over 4x, with lambda being n squared pi squared over 16, where n starts from 1. So there's a big difference between the Neumann condition and the Dirichlet. The Neumann condition has a constant term. The Dirichlet condition wouldn't have a constant term. Okay. Okay. Now what? Now you put them together and you get uxt as e to the negative 5 times n squared pi squared over 16t, not cosine, sorry, sine of n pi over 4x, where n starts from 1 through infinity. And what you want to do is you want to take linear combination of everything, so you put sigma of n from 1 through infinity of Cn. Okay. Now you plug in ux0 equals to 20, implies that 20 must be equal to sigma of n equals to 1 through infinity Cn sine n pi over 4x. Okay, so we're pretty close now, right? What does this mean? We want what? We want Fourier sine series. Right? So we want Fourier sine series whose formula is that Bn must be equal to 1 over L, actually 2 over L, integral from 0 to 2, f of x sine n pi over L x dx. So you have to compute this. But for us, L would just be 4. F of x is 20. Sine of n pi over 4 x dx. And this doesn't even need a integration by parts because it's just sine. So 20 can be brought outside. 20 divided by 4 is 5. 5 times 2 is 10. So you have 10 times the integral of this will be 4 over n pi with a minus cosine n pi over 4 x, and you plug in 4 and 0. And that's going to be negative 4 times 10 is negative 40, so it's negative 40 over n pi. And when you plug in 4, you get negative 1 to the nth power. When you plug in 0, you get 1, and you have to subtract those two. So that's your Bn. Okay. And therefore, now after comparing the Fourier sine series with this, you see that Cn should be exactly this one. Right? So what's the final answer? The final answer would be that uxt is equal to summation from n equals to 1 through infinity of negative 40 over n pi, negative 1 to the nth power minus 1, and e to the negative 5 times n squared pi squared over 16t sine n pi over 4. Now for this, what would you get as a solution if you'd send t to infinity? What do you get if you send t to infinity?
0.
0. Right? Yeah. Because if you have a bar and you put 0 at the endpoints, everything will be 0 at some point. So what happened? How long did it take? Like 10 minutes? Yeah. Just solving this one. Yeah. So it could be a one question on the exam. Right? You know, imagine having to do exam 1. Yeah.
Speaking of the exam, what's the best way to prepare for the exam later?
I'll make some practice problems for you. Yeah. But you know, you should at least do the homework problems that's assigned, and then it should be good. So this entire thing, like this one question could be like 50 points on exam 1, because it has like all these small parts. Or I could divide them as like this will be like 15 points. Finding the sign series could be 15 points, and then 20 points will be actually constructing the entire solution. And 5 more points to find out the limit when t is sent to infinity. So it gives you a good idea of what could be on the exam. All right, I think this is a good place to stop, although we still have some more time.